Ever pondered how your computer handles numerous tasks simultaneously without faltering? Today we'll delve into the fascinating world of process management in operating systems. Imagine a bustling city where every individual has a specific role to play. That's akin to an operating system where multitudes of processes work in tandem to ensure a seamless user experience. The key to this harmony? Process management. It's the conductor of the orchestra, the director of the play, the traffic controller of this bustling city. Process management is the heart of an operating system's functionality, ensuring that processes are created, scheduled, synchronized, communicated, controlled, and terminated efficiently. Every time you click on an application, open a document, or even move your cursor, there's a flurry of activity behind the scenes. Let's start with process creation and termination. Think of a process as a program in action. When you initiate a program, the operating system breathes life into it, creating a corresponding process. Once the program has done its part, the process is gracefully terminated, much like the curtains falling after a play. Then comes process scheduling. This is the operating system playing the role of a fair and efficient manager, deciding which processes get the CPU's attention and in what order. It's like a well-orchestrated dance, ensuring that no process is left waiting for too long. In a world of multitasking, processes often need to access shared resources concurrently. Process synchronization mechanisms, the peacekeepers, ensure that every process gets its turn, maintaining harmony and data consistency. Inter-process communication, or IPC, is akin to the postal service within an operating system, ensuring processes can exchange data and synchronize their actions effectively. The operating system also plays the role of a meticulous record keeper, tracking the state of each process. This is like keeping tabs on whether an actor is on stage, waiting in the wings, or has finished their performance. Lastly, the operating system controls processes, much like a director guiding actors, deciding when to suspend, resume, abort, or prioritize them. This ensures optimal resource management and system performance. And let's not forget memory management, the operating system's responsibility of allocating and deallocating memory for processes, ensuring efficient use of this vital resource. So buckle up as we embark on this journey to unravel the mysteries of process management. Imagine your computer as a bustling city, and the processes as its citizens. Every city has births and deaths, so does your computer. When you initiate a program, it's like welcoming a new citizen into the city. That's the birth of a process. The operating system creates a unique identity for this new citizen, allocating resources and setting up a comfortable environment for it to function in. It's a complex and intricate operation, but it happens behind the scenes every time you open a new application or run a command. Now, what about when a process dies? It's like bidding farewell to a citizen. When a program finishes its execution or is forcefully terminated, the process ceases to exist. The operating system reclaims the resources, clearing the memory space, and the process is no more. Just like a city, your computer constantly witnesses the birth and death of processes. Ever heard of the phrase first come, first served? Well, your computer uses a similar principle, with a twist. Let's talk about process scheduling. Imagine you're a conductor, and your orchestra is a swarm of processes. Your job is to ensure each instrument, or rather, each process, gets its turn to shine, all while maintaining a harmonious symphony of operations. That, in a nutshell, is what your computer's operating system does through process scheduling. It's like a maestro, deciding which processes get to use the CPU and in what order. There are several strategies, or algorithms, that the operating system can use to schedule processes. First up, we have first come, first served, or FCFS. Just like it sounds, this method gives priority to the process that arrived first. But it's not always fair. Imagine a long, complex process arrives first, and a quick, simple one comes second. The simple process has to wait for the complex one to finish, which can lead to inefficiencies. Next, we have shortest job next, or SJN. This one tries to fix the problem with FCFS by giving priority to the process with the shortest expected running time. But it's not perfect either. It can lead to longer processes being indefinitely postponed if short processes keep arriving. Then there's round robin. This one is a bit like musical chairs. Each process gets a fixed amount of CPU time in turns. It's fair, but it can lead to what we call context switching overhead, the time it takes to save and load process states. And there are many more. each with its own strengths and weaknesses, and each suited to different kinds of workloads. The choice of scheduling algorithm can significantly impact system performance, response time, and the user experience. So, process scheduling is your computer's way of deciding who gets to use the CPU when and for how long. Processes on your computer often need to share resources. But how do they do this without stepping on each other's toes? Imagine an orchestra, with each instrument playing its part. Without a conductor to synchronize them, the result would be a cacophony. Similarly, process synchronization in an operating system is the conductor that ensures each process plays its part at the right time, maintaining a beautiful symphony of operations. This synchronization is critical in ensuring data consistency. Imagine two processes trying to update the same data simultaneously. Without synchronization, they might overwrite each other's changes, resulting in data inconsistency. To prevent this, mechanisms like semaphores, mutexes, and monitors are used. These tools act like traffic signals, coordinating the processes to ensure they access shared resources without conflict. In the bustling city of your computer's operations, process synchronization is the traffic control system that prevents accidents, ensuring smooth flow and order. It's through this intricate dance of synchronization that your computer achieves harmony amidst the chaos of multitasking. Processes like people need to communicate. But how do they chat without mouths or ears? Well, they do so through a fascinating mechanism known as inter-process communication, or IPC for short. IPC is like the postal service of the computing world. It's how different processes send and receive messages, synchronize their efforts, and share data, all within the bustling metropolis of your operating system. Imagine a city, bustling with activity. Each building, each inhabitant represents a different process. They all have their tasks, their roles. Some are creating content, others are managing resources, and some are busy executing functions. But to make this city thrive, they can't exist in isolation. They need to interact, to share, to communicate. That's where IPC comes in. IPC provides the infrastructure for these processes to converse with each other. It's the roads, the phone lines, the internet of our city. It allows processes to exchange data, synchronize their actions, and even send signals to each other. It's like the glue that holds our digital city together, enabling cooperation and coordination among its residents. There are several forms of IPC, each suited for different scenarios. There are pipes, which allow for direct communication between two processes. There's shared memory, where multiple processes can read and write to the same space, a communal bulletin board of sorts. Then there are message queues, where processes can leave messages for each other, like a digital mailbox. And let's not forget sockets, the internet's favorite, allowing for communication over a network. IPC isn't just about data exchange. It's a dance, a rhythmic ballet of information flow. Each process carefully timed, each message meticulously coordinated. It's about ensuring that each process gets the information it needs, exactly when it needs it, without stepping on each other's toes. So, the next time you're using your computer, remember the intricate ballet happening behind the scenes. Every click, every command, every output is a result of countless processes communicating, coordinating, and cooperating. Through IPC, processes can have meaningful conversations, leading to more efficient system performance. From birth to death, from scheduling to synchronization, processes lead a complex life. So let's take a moment to reflect on the journey we've taken today through the intricate world of process management in operating systems. It's a realm full of complexity, but one that's absolutely vital for the smooth operation of our computers and networks. We started by discussing how processes are born and eventually meet their end. A program is nothing but a static file until the operating system breathes life into it, turning it into a dynamic process. And when the task is complete, the operating system ensures a graceful exit, freeing up resources for the next task in line. The scheduler then steps into the spotlight, acting as a conductor of a grand orchestra, deciding which process gets the CPU's attention and when. It keeps the harmony, using various algorithms like first come, first served, shortest job next, or round robin, each with its own strengths and weaknesses. Next, we delved into the world of process synchronization, where multiple processes share resources without stepping on each other's toes. Techniques like semaphores, mutexes, and monitors ensure a smooth dance, preventing conflicts and maintaining consistency. We then explored the art of conversation between processes, known as inter-process communication. Whether it's through pipes, message queues, shared memory, or sockets, processes communicate, share data, and synchronize their actions, enabling complex tasks to be distributed and completed efficiently. We also touched on process state management and control, where the operating system keeps an eagle eye on each process's state, making essential decisions to suspend, resume, or terminate processes for optimal system performance. And finally, we discussed memory management, a critical aspect of process life, where the operating system allocates and deallocates memory, ensuring efficient use of resources and the smooth execution of processes. The next time you switch on your computer, remember the intricate ballet of process management that makes it all possible.